Hello, welcome to my talk. This is Jiawei from the University of Minnesota. We propose a fast and robust place recognition approach for stereo-visual odometry. Recognizing previously visited place is an essential part of a SLAM system. It enables the robot to relocalize itself when it gets lost. It can also bring non-local trajectory constraints, which is loop closure, so that we can greatly improve the global trajectory accuracy. In the example on the right side, the car revisits the starting location as observed from those two images. While this is a relatively easy task for human, this task can be very difficult for robots. Among possible approaches, visual place recognition has been widely used. Robots can use an image to represent the place. The similarity between images determines if two places are very close to each other. The similarity between images is often measured by feature correlations, so we can detect features and match them across image frames. If images are taken at nearby locations, they are expected to share a large number of common features. Or we can check the spatial layout of the images. In this example, both images have high-frequency areas on the top right corner and the bottom left corner. Deep learning algorithms have seen increasing use in recent years because of their high accuracy. Training a deep neural network to automatically recognize places has also shown promising results. On the other hand, for LiDAR-based SLAM systems, the environment is represented by a 3D point cloud. Similarity measurement between point clouds are used for place recognition. To check the similarity between point clouds, a naive way is to simply align the point cloud. But for computational efficiency, we usually extract point cloud features and match the features across point clouds. Alternatively, we can use global descriptors to describe the entire point cloud. In this example on the right side, we use the maximum heights to represent the point cloud. Stereo-visual odometry generates 3D points with an absolute scale. However, 3D points are usually not used by conventional place recognition approaches. 3D points can be potentially more reliable than 2D images for place recognition. Global LiDAR descriptors can also be more efficient. Therefore, we explore the idea of using LiDAR place recognition approaches for stereo-visual odometry. However, there are a couple of challenges. The first one is due to the narrow field of view of cameras compared to the omnidirectional LiDAR. The 3D points from the stereo-visual odometry are distributed in a frustum, which is sensitive to the camera pose. The second challenge is the fact that 3D points from the visual systems are usually not as consistent as the points in the LiDAR scans. To overcome the first challenge, we propose a simple but effective approach to imitate a LiDAR scan from the stereo-visual odometry points. The idea is to cache the 3D points into a set of local points. For a new place, we found all points within the desired LiDAR scan range centered at the current position, which we referred to as spherical points. We filter the spherical points to improve efficiency and consistency, as these filtered points become the imitated LiDAR scan. An example of imitated LiDAR scan is given on the top right image. We can clearly see the structure of the environment. Subsequently, we apply LiDAR descriptors on the imitated LiDAR scan to get a signature for the place. One note is that this approach requires the camera to move forward predominantly so that we can continuously accumulate points into the local point set. We choose 3 recently developed LiDAR descriptors that have shown to be robust to inconsistent points. The first one is M2DP. Its high-level idea is given in the right figure. We first align the points to a reference frame obtained from PCA. We then project the rectified points onto multiple planes defined by the viewing angles. We further divide the plane into multiple bins by radius and azimuth, and count how many points are projected onto each bin. We concatenate the point count and get a projection histogram. Lastly, singular value decomposition is applied to the histograms to get a compressed place signature. We make the following modification to M2DP for use in our visual-based approach. When counting the points objected onto each bin, we also calculate the average grayscale intensity. We then binarize the average grayscale intensity by comparing it to the global average. The intuition is to highlight the bright bins. The second descriptor we use is scan context. The high-level idea is as follows. We first align the points with the gravity direction measured by an IMU. We separate the horizontal plane into multiple bins by radius and azimuth. For each bin, we found the maximum height. We then concatenate the heights as a signature for the place. To bring it to our visual system without additional sensors, we replaced the IMU measurement with PCA alignment as done in M2DP. Due to the PCA ambiguity, we switched to height range from maximum height. As M2DP, we also augment the descriptor with grayscale intensity information. One note is that scan context is primarily used for place recognition in urban settings. The last descriptor is called delight. In this approach, we align the points using PCA. Then we divide the LiDAR scan into 16 bins by radius, azimuth, and elevation. In each bin, we calculate the histogram of the LiDAR intensity. We obtain the place signature by concatenating the histograms. In our visual system, we replace the LiDAR intensity with grayscale intensity. Delight does not fully explore the 3D structure of the environment. We include it in our experiments to highlight the value of 3D structure for place recognition. In the experiments, we use SO-DSO, introduced in our IROS 19 paper, as our stereo visual odometry. We set the desired LiDAR range to 45 meters. We let the point structure descriptor to have twice as much weight than the intensity descriptor, as we rely more on the structure. We use the KITTI and the RobotCar datasets for evaluation. We focus on the area under the precision recall curve, or AUC, and maximum recall at 100% precision as our accuracy matrix. In KITTI dataset, each sequence was recorded within an hour. There's not much theme change when the car travels back to the pre-visited location. Therefore, backward and gist work very well. Even though our adapted LiDAR-based approach are not as good as gist and backward, both AUC and the maximum recall are not low. If we plot the recognized place on the trajectory, we found that our adapted scan context failed to recognize places in short segments. This is because the proposed approach needs the overlap trajectory to be long enough to accumulate enough points. This is one of the shortcomings of our approach. On the other hand, we can see the backward failed to recognize any place in sequence 2. This is because the revisited places are occupied by foliage. Backward failed because future matching is vulnerable to repetitive textures. However, our approach still works. One major benefit of using global descriptor is high computational efficiency. We can see that the adapted scan context runs much faster than the conventional approaches. It can even run in real time. Our second part of the experiments is based on the RobotCar dataset. It is very challenging for place recognition. The task is to recognize places across different seasons. The same thing in different seasons looks drastically different. Snapshots are given on the right figures. In the RobotCar results, which are quite different from the KITTI outcomes, the adapted scan context is the most accurate and robust approach for both AUC and maximum recall, which is further validated by the precision recall curves. If we plot the results of place recognition from spring to different seasons, we found that the adapted scan context is the most robust approach against seasonal theme change. We also studied the contribution of augmenting the descriptor with grayscale intensity information. This table shows that even though the intensity descriptor itself is not very robust, it can further improve the accuracy of the structure descriptor. To use the proposed approach, a stereo camera is required to ensure an accurate scale of the point clouds. Furthermore, forward motion is required to accumulate points. But compared to the conventional backward approach, our method is more accurate and robust to visual appearance change, and much more computationally efficient. It is also robust to repetitive textures. However, for backward, it is more accurate when there's not much appearance change. Here is a demonstration of this work. The green dots are our imitated LiDAR scans from the stereo visual odometry. Here are the links to our implementation and the project page. Thank you for your attention.